All right, so let's continue. Uh, Now we will look at the issue that we have with digital arithmetic, right? So because we have limited space in digital electronic. So for example, if we have a 4-bit adder, right? 4-bit system, and if we use the sign number, okay, so the result will be from what value to what value, because of course if we have unsigned value for 4-bit system, yeah, so the range of the result must be from 0 to the maximum is 0 and the maximum is 15, right? What if we have the result more than that? Okay, so for 4-bit system in sign representation, we can see that the number that we can represent is this. Only the maximum one is positive 7. Yes, of course. Yeah, positive 7, which is 0, 0, 0, 1, 1, 1. All right, this is positive 7, the biggest positive number that you can have or you can put in 4-bit system. All right, if you put 1 here, this is not positive number already. This is negative number because the sign is 1. All right, so the maximum number for positive number should be 0, 1, 1, 1, and this is actually 7. And for the minus, the number that is the smallest number that you can represent using a 4-bit system is 1000, which is minus 8. Right, 1000, this is minus 8 in uh, decimal. Right, and this is minus 1. 1, 1, 1, 1 is actually minus 1, and the minimum is minus 8. What if we have something like this? We have plus 5 plus 3, positive 5 plus positive 3, or 5 plus 3. So the result is 8. All right. So 8 in binary is 1000. But this, you can see that you cannot put in a 4-bit system because this represents sign bit already. All right. Means that positive 8 cannot be fit in fitted in the 4-bit system, right? You can see the maximum number that you can use is positive 7 only, right? So meaning that you need a bigger system. And if this happen, yeah, when you do the arithmetic and you have the result that is not fit in the system that you have, in this example is 4-bit, right? It is called an arithmetic overflow. arithmetic overflow. Okay, and you can see that here the range for a 4-bit system is from +7 to -8 to +7, right? So this is actually 2 power of n minus 1, and this is actually minus 2 power of n, right, where n equal to the size of your system. In this case, sorry, n minus 1, yeah. In this case, n equal to 4, so you have 4 minus 1 is 3, 2 power of 3 is 8 minus 1, you have 7, and in this case, minus 2 power of 3 is minus 8. So this formula is always correct when you change to another or bigger system. For example, if you have 8-bit system where n equal to 8, so you have the maximum number for 8-bit system for positive is 2 power of 7 is 1 to 8 minus 1, you have 1 to 7, right? So in this, for negative is minus 1 to 8 always. And if you have bigger system, for example 16-bit, so the maximum is 2 power of 16 minus 1, and this is also the same, right? And the issue now is that, if we have the result that is not fit within the significant bit that is used to represent the number, so it is called an arithmetic overflow, right? So this is the example. If we have 7 plus 2, and 7 plus 2 is 9, and 9 is actually not fit in the 4-bit system, because remember, the maximum value for the 4-bit number is 7 for the positive part, and for negative side, minus 8 only. So plus 9 is not fit. Why not fit? You see here the result. When you add 7 plus 2, you have this, and look at the sign here. This is negative. All right, so the positive plus positive, the result must be positive, right? But you have negative number here, so this is wrong, and this wrong is called overflow. Okay, look at another example. If we have minus 7, and this is minus 7 in second complement, this is number 2, we add, and this is minus 5, and minus 5 is okay. This is minus 5 is okay because it's within the range. Remember, the smallest negative number is minus 8. Minus 5 is larger than that, should be okay, right? So no overflow. Here, plus 7 minus 2, you have 5, and 5 is okay because less than 7. And when you add in binary, you can see that, this is positive, and this is 5, and this one is ignored, right? We ignore this 4-bit. Look at the 4-bit only. Minus 9 should be overflow, right? Because this is smaller than minus 8 already. So when you look at this, when you add this, you have this. 0 indicate that the result is positive, but it is actually negative. That's why we call it overflow here. Okay, so this overflow is very important in digital system because remember, the digital system is limited. We have either 4-bit or more than that, but we have a limit number, finite number, right? We have either the biggest now is 1 to 8, right, system. You can have more than that actually, but the cost is very high. Yeah, so we have 16-bit computer today, means that we have a 16-bit adder inside there. So what happens if the result of the add operation is more than 64-bit? Okay, so the computer need to know that, because we need to produce the output, and the output should be there, should be possible, right? But the hardware should know that if the result is overflow, what to do. Okay, so for example, if we have overflow, maybe the result should be stored in a bigger location in the memory, for example. All right, so one memory location not enough to store the result, so you can use more than one memory location. Okay, but the system, the hardware need to know that, such that it can process it correctly, right? If not, you will get the wrong result later on. Okay, so this is the concept, the issue that we will face when we design in digital. Now we need to handle this. So how to handle this? Of course, we need to design a hardware, a circuit that can detect whenever this happen, right? And remember, we are the designers, so we will convert the concept. This is the concept to the hardware. Okay, so now how to create the hardware to detect this? So we can observe one thing, which is C3 and C4. What is C3 and C4? C is the carry bit. All right, so remember the C, the adder here. This is C3 and this is C4. We can name it C4, right? The carry from this, the add operation, we have this. The carry from this add operation, we have this. Let's observe this. First case, we have overflow. All right, so we can have something like this. We can have C4, we can have C3, and let's label the overflow as V. Okay, so C4 and C3 can have 4 possible combination, because this is 2-bit, 2 number. All right, so we can have 0, 0, or we can have 0, 1, or we can have 1, 0, or the last one must be 1, 1. Right? And look at this. If this is 1, 0, yeah, C3 equal to 1, and this should be this case, right? So we have overflow equal to 1. This case, 0, 0, when C4, C3 equal to 0, 0, we don't have any overflow. If this one, 1, 1, means this case, we don't have any overflow. But here, if 1, 0, this case, we have overflow. If you change this number to other than this, you will have the same result here, right? So you can try for other number, you will have the same result here. Means that this is true for all number within the range, within the 4-bit system. Now we have this, meaning that we can actually detect the overflow using the XOR gate, because this is XOR behavior. All right, C4, C3, and we have V, or overflow. So to create the hardware to detect overflow is easy. We can use XOR gate, right? So this is XOR, C3 and C4. So if you have a bigger adder, for example 8-bit, so it will be C, yeah, this is 8, so this should be C8 XOR C7, right? It's correct also. Okay, so that is how we detect the overflow in our circuit, in our system. All right, that's it. Any question? Anyone? All right, so if no question, we move to the next circuit, which is the comparator. Comparator. Uh, so the comparator is very important in computer system, in the digital system, right? Where we'll always compare number, right? Remember, if you program in your computer, right, you do comparison a lot, right? So for example, in your program, you write if a equal to 0, means that you compare a to 0. Or you can have a, if a more than 0, if a more than 2, you do this, else you do this. So you compare. All right. So this is in program, but inside your computer, in your computer, you need a comparator. In order to do that, a circuit that can compare number and give you result whether a is bigger than 2 or less than 2. All right. So for example, if you have two value a and b, okay, so you should be able to compare, and your system give you whether a greater than b, or a less than b, or a equal to b, right? So that circuit is called a comparator. Now how to do the comparison? There is many way, and the easiest way, and the one that is used in the computer system is using again the adder. So you can see that the adder can do many things now. First, of course, it can do add, it can do sub, and last one, it can do comparison. How? Look at this. If you want to know whether a is equal to b, or a is greater than b, or a is less than b or not, what to do? So in math, in mathematics, right, if we want to compare a number, we can actually sub the number, right? Subtract. So for example, if we have a minus b, if the result, the answer is positive, what is the conclusion? Come on, give me the answer. If a minus b is positive, yeah, any a, any b. A can be any number, b can be any number, but if we have a minus b and the result is positive, What is that mean?
That mean A bigger than B.
Yes, correct. So this means that A greater than B. Correct. And if we have A minus B, the result is negative. That means A less than B, right? And if we have A minus B is 0, means that A equal to B, right? So we can see that we can use subtract. And remember, our subtractor is built from an adder. That is why I said that the comparator is actually come from the adder. We use adder to create a subtractor as well. And remember, if we have the for example, back to our 4-bit adder like this, 4-bit subtractor like this one. Yeah, we have remember we have not gate. That is why check say that we use adder and subtractor, right? Because we have full adder and not, right? Because we have full adder and we have the not gate here, and this not gate is actually to get the second complement of y, right? If this is x3, y3, this is x2, y2, x1, y1, x0, y0. And here, what is the number that you need to have? What is it? Should be? Not should be, must be. Must be number 1 to perform sub, right? Because this complement, y complement, you need to add to this 1 to have your second complement. And this means x minus y in this case, x minus y. And now, how do we know that x equal to y? So must be all of here must be 0, right? Must be 0. And what is the gate, or what is the circuit that can only give you 1? Yeah, so we need to connect this all to a circuit, to the gate logic circuit. Yeah, we connect this all to this logic circuit, and this will output we call it Z. Yeah, 0 to detect 0. So the output Z equal to 1 means that all are 0. Means that whenever all of these output are equal to 0, then this z equal to 1. Means that we know exactly that x and y equal to 0, is equal. X and y is equal because when we do the subtract, the result here is 0, 0, 0, 0. This only means that x equal to y. But what is the circuit that we need to use in order to have z equal to 1 when all of these are 0? Which is actually easy. You can have, yeah, if we call it, this is s, s3, s2, s1, s0, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 1 until you have all 1, 1, 1, 1, right? And the output z is 1 here and the others are 0. So what is the circuit? Anyone? What is the circuit to give you this kind of output? Should be, oh come on, should be D. The answer is right here. Yeah. What is the circuit? No, 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 no. What is the gate here? Come on, Zaim. This is, yeah, check. This is a NOR gate. No, not all. All right. So the answer is no. A NOR gate give you Z equal to 1 whenever all of these are 0. Means that if our circuit, our comparator, if we have Z equal to 1, whenever Z equal to 1, the only conclusion that we have is that X must be equal to Y. All right. Because if other than that, if Z equal to 0, means that we don't have any result, 0 result here. Means that can be any number except all are 0. So means that the number is not equal already. Okay. That is the case for X equal to Y. Now, if for example Z equal to 0, means that X is now not equal to Y. So can have two possibilities, whether X more than Y or X less than Y, right? So how to check that? So remember, this is the key. Right? So if positive, the result is positive, means that X is more than Y. So how to know that the result is positive? We can use this line, yeah, the sign bit. So this, one is of course go to this input, and this you can straight away check this value. If the value is 0, means that the result is positive. And if the result is positive, the only things that we can say is that X must be more than Y. But if this number, this value is 1, means that the result is negative. And if the result is negative, means that X less than Y. All right? As simple as that. So in a computer system, to compare the circuit that compare the number is this. Yeah, we call it a comparator. And this bit is called n. Yeah, so when n equal to 0 means that the result is positive, and if the result is positive means x more than y. If n equal to 1 means that the result is negative, and if the result is negative means that x less than y. Okay, so we have this circuit. See, this is n, and we have another one. This is to check for the overflow. Remember C3 and C4, if we connect to the XOR gate like this, we have the overflow. So this is for negative check. Negative is for whether the result is negative or positive, and this is for zero check. Yeah, if the result is 0 means that x and y is the same, equal. All right, this is the comparator. And yes, you are required to derive the Verilog code for the comparator. So I think, yeah, I changed my mind already. Instead of designing this, I want you to design this for your assignment. All right, so change from adder subtractor to the comparator circuit. All right, now multiplier, we don't have time actually, so this one we can continue next week. All right, and this is I think should be sufficient for your exam, for your test, midterm exam.